So here we go. Oh, let's wait for that. Yeah, I could. And take a look at this question, because it kind of hits all the things that are a part of a kind of a standard mass spectrometer problem. You'll notice here that there's a indication of the direction of the magnetic field. You see how the dots are there laid out, but also off to the right. You're going to see that there's some information about the out of the paper in both regions. It is very common for them to provide you with reference for direction in addition to the symbology that they use for the reference. Don't be thrown off by it. But also note that you might see something that looks like this on your paper. I couldn't find one in a cursory glance. And they'll put something on the paper that looks like this, where they're telling you all the positive directions by giving you a three-dimensional axis somewhere on your picture, which means that in the problem, when they refer to things in positive, negative, they're wanting you to refer to this as a means of doing it, and they don't have to tell you that's what they're doing. You're supposed to know that if you see a coordinate system displayed, they are identifying their positive directions. Does everybody follow along with that okay? So it's been a long time since they just put that out there and said you need to know from that picture what direction is positive, but they still could do it. So I like to make sure I at least spend a minute talking about that. All right, so as an ion of mass m charge of unknown magnitude q is observed to move in a straight line through a region of space in which the uniform magnetic field points out of the paper and a uniform electric field points towards the top edge of the paper. As shown in region 1 above, the particle travels into region 2 in which the same magnetic field is present, but the electric field is 0. In region 2, the ion moves in a circular path of radius r as shown. Indicate on the diagram below the direction of the force on the ion at point 2 in region 2. Before we do that, we'll do it this order. We talked about this yesterday. When you draw this arrow in, they are looking for something particular. So all of you take a moment and draw in the arrow that you would draw for the depiction of the force on the particle. This is not a right-hand rule question. You don't know the charge of the particle. This is a circular motion question, and that's all it is. So I was just noticing about 10 of you getting your right-hand rules out. The only direction that force can be for it to go in a circular path is towards the center of the circle. That is the only direction it can be, which has to be perpendicular to the velocity at that point. The velocity has to be tangent to the circular path. I'm reinforcing this because I have a collection of people who are not taking mechanics here, but all of you had access to physics in a prior year. This is a circular motion question. They want you to realize that the unbalanced force has to be towards the center of the circular path. Now is everybody good with that? Because the next question is about, is the ion positively or negatively charged? So now is a right-hand rule question. You see what I mean now? So we don't want to be thrown. We don't know. So I'm going to put my pointer finger in the direction of the velocity because I know the velocity. But instead of trying to align my middle finger, I'm going to consider putting my thumb in the direction of the force and see which direction my middle finger lines up. And I'm noticing that if I put it in there, my middle finger points into the page. But we are told the magnetic field points out of the page. That suggests to me that my particle must be negative. Right? Because the only way a positive particle could curve in this way is if the magnetic field pointed into the page. So my particle must be negative. Now, here's the thing. Explain clearly your reasoning on which you based your conclusion. Yes, sir?
I know my you have to so I'll ask after.
All right. Your reasoning has to reference the right-hand rule. Now, you are welcome to also reason the left-hand rule. Because especially in the 70s, they were okay with that. But you don't have to give that much explanation here. So all you really need to say is that by use of the right-hand rule, a positive particle would bend in the opposite direction. Or by use of the right-hand rule, the magnetic field would have to point into the page for the particle to curve in the indicated direction. Therefore, the particle must be the opposite sign, negative. A single sentence, but in that sentence, you do need to reference the right-hand rule. But that's all you have to reference. Saying right-hand rule is enough of an indication to the person grading the paper that you understand how the right-hand rule has to be applied. They'll know whether you got the right answer or not, but it's a 50-50 shot. But you have just say right-hand rule, and half the time, that's adequate justification. What you don't have to do is explain what the right-hand rule is. You don't have to say, I pointed my pointer finger in the direction of the velocity and my thumb in the direction of the force. You don't have to do any of that. Does that make sense? This is the first time where I would tell you to say less is more in this explanation. Yes, sir?
After we mentioned the right-hand rule, can we just say that using the right-hand rule, the magnetic field points inwards to outwards, and that's it? Maybe add more.
I think you have to explain why you know the particle's negative from your application of the right-hand rule. If you think that that does that, okay, but I found that to be a little bit convoluted. Like if you say if I align my hands with the direction of the velocity and the magnetic field, it shows the force points outwards, but the force here is clearly inwards. That must mean the particle is negative sign. That's fine. So if you want to reference the direction of the force as opposed to the magnetic field, that's adequate. All right, that one's not too bad, but that's, you see how the right-hand rule is going to be applied in problems. Yes, sir?
And couldn't you also use the first picture they give you, since it's the same thing? They said they have the magnetic field is the same in both, but there's an electric field in one. So since the force is going upwards in the second region, that means the electric field has to be exerting a force downwards, and so it has to be a negative particle since it's going against the electric field.
Okay.
Would that also work?
I don't see why it wouldn't, but I think it's a lot more words. But I don't think there's anything wrong with it. I mean, the thing you're talking about is what you're going to have to do for question E. So they're directing you to that by the end anyways. So I don't think there's anything wrong. I mean, you're just kind of jumping ahead a bit. C, indicate and label on the diagram below the forces which act on a particle at point 1. So this is what we're getting at with what David told us. So I think that one's not particularly hard. We already know that the magnetic force must point upwards based on this. Now here's where I'm going to say to David that he needs to be careful. The electric force has to point downwards here. Correct? Would a positive particle have a different set of forces if it passed through here? A positive particle would still pass through this same region without being deflected, correct? It would experience the same balanced forces, but they would be flipped. The electric force would be up and the magnetic force would be downwards. But a positive particle would not be deflected in this area in the same way that a negative particle would be deflected. So using that as a means of justification is more ambiguous, because this is not a way to tell whether your particle is positive or negative. If you have an unknown charged particle enter a region of space that has a balanced magnetic and electric field, then you don't know whether that particle is positive or negative because it's not deflected. You understand why you have to be very careful about how you word that? In the other region, we have a clear known direction of the unbalanced force in the particle due to only one field, the magnetic field. That's a clearer place to figure out what the charge of the particle is. Okay, find an expression for the ion speed v at point P1 in terms of E and B. All right. I'm going to just do that right here, and I'm going to zoom all in so we know that we have two forces that act there. We have the magnetic force upwards coming from Q V cross B. What's an expression for the electric force?
EQ.
What's that?
EQ.
Yeah, I'm going to say Q times E. It's more traditional to write the Q first. We know that this net force has to equal 0. So QV cross B equals QE. Is there anyone here who will have a problem with me saying that this is QVB sine 90 degrees? Based on the picture, the velocity and the magnetic field are perpendicular to each other. Now we're solving for the velocity, but please pay very close attention. You cannot use this to determine what the charge is at all. The charge cancels out here. So because of that, this is not a particularly good way of figuring out what your charge is. This arrangement selects for velocity. It doesn't select for mass, and it doesn't select for charge. So you'll hear me say that phrasing before. Select for velocity means that a particle of a specific velocity will pass through. If you go back to that picture and look, if our particle has a slower velocity, well, then the force from the magnetic field will be less because V is smaller, right? So if we look at it in this region, say right here, the particle is at this moment right here, but its velocity was less than before. So this is a slower velocity. The electric field is going to be the same size as it was before, right? Because the electric field has nothing to do with how fast it's going, but the magnetic force will be smaller because the velocity is smaller. QV cross B. Q didn't change, V was smaller, so the magnetic force is less. This particle will curve down and strike the wall. The particle goes faster, then the magnetic force will be greater than the electric force, and the particle will curve up and strike the wall. This arrangement of balancing the electric field and the magnetic field selects for a specific velocity. So if I want to change the velocity that I'm selecting for, I can adjust the electric field, and that will select a different velocity. So that's what I'm trying to say here is that the velocity that the particle has to travel straight through that area, that region, has to be very specific. This is called a collimator. It will ensure that all of your particles passing through a region are selected for a specific velocity so they all come out at the exact same velocity. If you're trying to send particles into an accelerator and they all have to have the same energy, then you want to ensure they have the same velocity. This is how you do it. Does that make sense? So this is a velocity selector. All right, so let's look again. Question E, starting with Newton's law, derive an expression for the mass m of the ion in terms of B, E, Q, and R. Starting with Newton's law, derive an expression for the mass m of the ion in terms of B, E, Q, and R. So let's do this over here by the picture. They say start with Newton's law. Which law are we talking about in region 2? So, do you have a question or you want to answer? Go ahead.
Net force equals MA with the centrifugal.
Yep. Net force equals MA. See, that's what they mean. If they say derive and they specify the law, you had better write the law out. Don't skip. Do you understand what I mean? Don't even substitute v squared over r in yet. Start here, please. Then make sure you do your substitution. We can go one step further too, because we know this has to be QVB sine 90 equals mv squared over r. And we can cancel out one of the v's. That's convenient. However, we can't have v in our answer. Although we're looking for m, and we can solve this for m quite readily right now, m is going to be equal to QBR over, nope, it's just QBR, isn't it? Oh, QBR over V. There. We can't leave it like this. Why can't we? Yeah, V is not allowed to be in our answer. But we solved for V just a moment ago. We can substitute what we used for V in the prior part here. This will eliminate V in the question and give us QB squared R over E. So, a couple things of interest here. A mass spectrometer is a device that would select for mass. This would select for mass. I don't know if you understand how it would, but the R that we get here corresponds to a specific mass. So all things being the same, meaning same electric field, same magnetic field, and same charge. As a particle passes through here, a particle with more mass wouldn't land in this spot. Particle with more mass would land somewhere else. Probably would have more inertia, and more massive particles would hit over here. And particles with less inertia would hit over here. So we call this a mass spectrometer because it selects masses. If you put a detector here, you could allow particles to stream into this room, and by the number of collisions that occur in every place along that wall, you could start to stratify and figure out what the masses of your samples are. Yes, sir?
Does a mass spectrometer have to have a constant velocity?
In this example, yes. You would want the particles to come in all at the same velocity because you know that is already selecting them for, you're evening out all the other factors that would contribute. But there are other types of mass spectrometers that don't require that. So, like a bubble chamber. Has anybody ever heard of a bubble chamber? A bubble chamber is a chamber that is filled with like soap bubbles. And as the particle passes through, it creates bubbles as it passes through the gas, and you can get a track of the particle. And from its radius of curvature, you can determine the mass of the particles. They can be coming in at any velocity that you like. So I'll show a picture of a bubble chamber tomorrow. Before we get into this problem, let's remind ourselves a little bit about the force from a magnetic field. And still, I have no idea why it's a B, but it doesn't really matter. The force from a magnetic field, and I need to be very clear because I don't always, and I gloss over things that are important. This is the force on a free particle as it passes through a magnetic field. And I'm trying to be very careful because in a moment, when we finish this problem, we're going to talk about the force on a current carrying wire, which is where things actually get to be useful. The force on a free particle, it might be less useful. And although we have created objects that have utilized this in the past, it's not as interesting as some other things that might be out there. The first thing I want to point out, and I haven't talked about this at all, is the B field itself. The unit of the magnetic field is the Tesla. or the Gauss. They are not the same unit. 1 Gauss is 1 times 10 to the negative 4th Tesla. So a Gauss is a small measurement for the magnetic field, and Tesla is actually a pretty large value for the magnetic field. When we talk about a 1 Tesla field, 1 Tesla field is strong enough to begin to erase things that are on magnetic tape. 2 or 3 Tesla magnetic field can begin to erase things that's on more permanent forms of electromagnetic storage, like solid state drives, things of that nature. 3 Tesla fields can start to mess with your brain waves and the motion of electrons in your body. So a 1 Tesla field is a big field. It's hard to generate a field of that size. Now, from this calculation alone, you should be able to figure out what the units of the Tesla are. They are not obvious. So let's take a look at the unit of a Tesla. Force is Newton, charge is Coulomb, velocity is meters per second, and then we have the Tesla. So a Newton is a kilogram meter per second squared. So you'll notice that just this quick little thing, we can cancel out the masses, cancel out one of the seconds, and we can then kind of solve this for Tesla, and we get that a Tesla is 1 kilogram per Coulomb second. We will also define the Tesla using current later in the week or probably early next week, but the unit of the Tesla doesn't have any obvious reference, I don't believe, to what it is. In the same way that we didn't have a unit for the electric field. We didn't have a named unit for the electric field. It was Newton per Coulomb or volt per meter. But we do name the magnetic field in honor of Nikola Tesla, not the car, the scientist. And are any of you familiar with the story of Nikola Tesla?
Yes.
Because it is quite tragic. So if you have a chance, I used to show a movie every year when I used to show movies, and it had to do with the battle that took place in which Nikola Tesla and another famous scientist, Thomas Edison, were fighting over contracts for New York City to provide power. And Tesla and Edison had very different ideas about how to provide power to homes. And the market was lucrative. The problem is Tesla was not a businessman, and Edison was an excellent businessman. Excellent scientist, but a horrible person. So if you look at the history of Edison, we tend to worship Edison as an amazing inventor. Many of his inventions were built on the backs of other people's work. So things that we give him credit for, like the incandescent light bulb and a few other things that he's developed, he actually didn't invent those things, other people did. But Edison had one thing going for him. He was already rich to begin with. And with that money, he was able to buy a lot of things. So if you look in the past of Edison, Edison has done some great things for the country. I'm not trying to minimize his contribution to the United States or to science in general. If you look up, there's a museum in southern Florida dedicated to Edison, Goodyear, and Ford. And the story behind them trying to produce cars here in the United States is also an excellent story. They were here in Florida trying to see if they could grow rubber plants in southern Florida, because at the time we could only get rubber imported from China. And trade relations with China have not always been good in our past. And we're kind of continuing that even now. So, we do have that. But the story about Tesla and his method of trying to provide electric power versus Edison's method of trying to produce electric power is interesting. Tesla's one. The method in which we have power delivered to all the homes in the country is Tesla's method, which is alternating current. And his work in the areas of alternating current, magnetism, and his applications of Maxwell's laws to the distribution of electricity is incredible. he even developed a method for generating electricity through the air. And I know that that seems like no big deal now, like you just put your phone on the pad and it will charge up. I'm not saying that. I'm saying he put a tower in the middle of a neighborhood and the houses draw the power directly out of the air from a tower a couple hundred yards away. So if you look at some of the things that he was successfully able to put together, they're amazing. But he was a scientist, and he was also deeply emotionally and psychologically flawed. And those caught up with him later in his life. So it's some of his contributions were actually not attributed to him until later in life. Later after his death, because when he died, his students, and I use that word loosely, people who worked with or around him, stole his work and published it as their own. Our ability to receive radio waves and use radar is largely attributed to some of the early work he did in the generation of RF waves. So if you have interest in Tesla, you should probably look up some of the stuff he's done. He is, like I said, an incredible scientist, but again, a person who had some deep flaws on his own, which I think is a good lesson for us as people who try to study science. The only thing I do want to say about it is that I was fortunate enough to work in a nuclear accelerator during a project for one summer, which I never repeated. But I remember we were working with a 3 Tesla or 4 Tesla magnetic field as part of the particle accelerator in a cyclotron, and I watched it pick up a 32-gallon trash can and whip it across the room. So magnetic field. When we talk about a Tesla worth of magnetic field, it's like talking about an amp worth of current. So, when we try to look at the size, most magnetic fields you'll ever come in contact with will be in the tenths of a Tesla or millitesla. 1 or 2, 3 Tesla fields. You're getting MRIs. There's a reason why I had to take all the metal off, because you could have been hurt by it. It wasn't going to jerk it out of your ears, by the way. The type of magnetic field, the way they were using a magnetic field in a device like an MRI machine would more likely just make the metal get hot by generating a current through the metal due to induction. So they make you take things like earrings off and stuff like that so that you don't have that kind of problem. All right, so let's go back